Everyone, I think I'm going to go ahead and get started. Today we'll be discussing some of the theory behind GAN, some papers that he points to, and some kind of interesting applications or use of the adversarial laws, as well as theory, but theory from different angles that tries to explain GAN. And let me know if you can see my screen with the slides.
Yes, can see.
One more thing before we get going is I kind of appeal for volunteers for either doing the homework or future lessons. So if you can, please do so, because otherwise, at least next week, I won't be able to do much on this front and running out of people who are stepping up. So request for anybody who's interested in continuing sessions. Okay, so for those of you online who have kind of joined the NYU course on deep learning, that's very heavily focused on an energy model perspective. So I believe one of the lectures, or maybe even a little more than one lecture, was devoted to looking at GANs in the light of energy models. And this, the first few slides that we discuss in this course, or this portion of the course, also focuses on GANs as energy models. And the derivation for the adversarial loss equation or the GAN equation we have seen before from an energy model perspective. But I would encourage people who haven't watched that, and I'll try and post the link to the appropriate course lecture of that series. But there's a NYU Deep Learning with PyTorch course that covers a lot of ground, not just on GANs, but they cover most of it from an energy model perspective. So what is the concept of energy models? And one thing that at least I didn't know of that the lecturer talks about, the professor, is apparently energy models were all the rage between 2004 and 2011. And there's a lot of discussion of Boltzmann machines, and he says something called the wake-sleep algorithm and things like that, which was very heavily oriented towards an energy model perspective of machine learning. And then it seems apparently it went off to sleep, in the sense that it wasn't all that relevant. But Jan LeCun, one of the famous lecturers and people who came up with original MNIST sorting and that kind of stuff using machine learning, he's very much into the energy model perspective. So it's again had resurgence in its use. So the fundamental concept of energy models is, instead of viewing things as probabilities and likelihoods, you view it in a kind of thermodynamic view of the world. That is, there are many possible ground states for what you're considering, and such as an image, and the each of the ground state has an associated energy. And at least for me, what works is thinking of the energy concept as kind of inversely proportional, if you will, to the probability. So if a particular value is supposed to have a high probability, then you can think of it in an energy view as it having a very low energy, and vice versa. So low probability is high energy and high probability is low energy. And the relationship is kind of shown here. So if you think of it in terms of, GANs, images, and so on, the concept would be anything that you are highly likely to observe. If you have that image, then that is supposed to have a low energy. And any image that's not likely in the distribution is expected to have a very high energy. And the key thing is this normalizing constant that you need to consider. And That's an important thing to keep in mind, which normalizes this energy over all of the, if we keep referring to images and over all the images that you're likely to see, not just the likely images. The challenge with the energy model view of the world is the fact that the domain of the, for example, if we were to look at images, then the domain of X, where X is an image, because it has large, if X were an image, it has, let's say, even a small MNIST image, which is 28 by 28 by, let's say, 3-channel instead of binary. Let's say it's a color image, a color MNIST image, it's 28 by 28 by 3. If we assume that each pixel is represented by 8 bits, which is not even that high of a resolution, then the total number of possible values, it becomes very, very high. This is 10 to the power of 16464. So if you enter this, for example, it says in your calculator, that's equivalent to 256 to the very high power, and it just doesn't even calculate. And one of the trivia you learn listening to the lecture is apparently the total number of atoms in the universe is 10 to the power of 80. So you can see how large this figure is compared to even the total number of atoms in the universe, which is just 10 to the power of 80. So it's a very, very large number. So what that means is computing or calculating Z is pretty impractical. So what we need to do then is to approximate the Z. Now, since this is just an introduction in an abstract way, let's kind of make things a little bit more concrete in order for us to kind of focus on how we'll go about calculating Z. And we'll use many of the same techniques that we've kind of learned in the implicit models and variable adversarial or things that we have learned before. So if we look at an energy model, but where let's again continue to think of X as an image, goes through a series of neural network layers, and out comes the energy, and it's parameterized with data. And if we again look at it in a probabilistic sense, we are saying maximize the likelihood of X from the distribution of the data log of p theta of X. You substitute p theta of X into this same equation, but make it an energy oriented expression, then you say that translates to this second part. And subsequently, what this reduces to is the equation that we have here. Okay, so you see that this particular equation translates then to what we have on the right here. The important thing to note is Z, which is the normalization constant, is also a function of the theta. That is, it's a function of the parameter. And what we have already seen is Z is, because of the dimensions involved, even in a simple case, Z is quite hard to compute. So one of the things that one could think of is, let's say we forget this portion of the equation, and let's say we focus on just the first part. There's something which, again, the lecture covers nicely with some visual portrayal in the NYU course. The issue with just ignoring the normalization and viewing just the maximum likelihood and therefore the minimization of energy, if we were to take this approach towards our traditional problem, then what happens is the easy way for the network to solve this equation is to make the energy of all of the points very low. So without the normalization, the issue is that the energy that for all images would be very low, in which case what happens is you are unable to distinguish between the desired images, which should have the low energy, and kind of the non-likely to be seen images, again, keeping GANs in mind, the images which are good are the ones which are supposed to have low energy, but what our network will do is it will make all of the images have low energy. So again, the point being that this normalization is therefore important, and we need to kind of incorporate it in our equation to get it to work out properly. So that means we can't compute Z, which means we'll need to kind of approximate Z. And what we traditionally do is approximate it with Monte Carlo sample estimate. And so we again reach out into our bag and pull out the same set of tricks that we've used before of importance sampling rather than just regular sampling. That makes our likelihood of getting good samples in the sense that with a small amount of samples, we are likely to get a reasonable approximation of this quantity Z. And also we bring in the concept of variational distribution, and those things combined make the samples come to us from the right distribution, which means we are now able to approximate Z. So what this equation does is try to derive, and we've kind of seen a variant of this. It's just a traditional thing we've seen in variational autoencoder and its derivation. But log of Z, the definition of it is log, and it's log sum over all of the images. And a sum, in a way, is similar to an expectation. So log sum X belongs to, say, the distribution of all of the images, e to the minus e theta of X. And then we use this variational distribution, importance sampling concept, multiply and divide by the same. That converts this top numerator into an expectation. So this becomes log expectation X over the distribution Q of phi. That's the distribution we introduce. And it becomes e to the minus e theta of X divided by Q phi of X. Now, here we apply the Jensen's equality, which says log of the expectation is greater than or equal to the expectation of the log. And this is, the picture that, if you recall, basically it says that this point, which corresponds to the log of expectation, is kind of above always this other point that's the expectation of the log. Therefore, you get this greater than or equal to sign once you apply Jensen's inequality here. But this greater than or equal to is for all Q phi, and at the point of maximal or optimal Q phi, this inequality turns into an equality. And what this means is, at the optimal Q phi, this equation becomes maximum of, and these two, even though in the slides it's shown as a sigma, it's actually expectation as he corrects it in the lecture. So going through this derivation and what this equation turns out to be for for optimal Q phi, it becomes max Q phi expectation X from the distribution Q phi minus E theta of X. And then when we take negative log of Q phi of X, that's just the definition of the entropy of the distribution Q phi. And that's why this second part of the equation is just simplified to be an entropy of Q phi of X. So that's what this Z turns out to be using a traditional importance sampling, variational distribution techniques. And if we now, negate log Z, then you need these two, the sign of the right hand side flips, and the greater than or equal to becomes less than or equal to, and you end up with this equation. Now, right, so what did we actually do here in a kind of intuitive sense? We started with a Z which is kind of uniformly distributed over all possible X's. The samples that we'll draw from that Z will not be very informative, as we have seen before. And so we choose the correct variational distribution Q phi, which will yield us with a small number of samples, a decent estimate of Z. And then we substitute that, the derivation of that back into our original equation. And what we end up with in the original equation, which is this guy here, is the thing highlighted in the red box. So it becomes the first part remains, which is max theta Ex P theta minus E plus the minimum over Q phi of Ex from the distribution Q phi E theta of X, and then the negative of the entropy of the Q phi distribution. So what this tells us is the first part of this equation, this X comes from the data. So that you can begin to see is much like our GAN equation. The second part of X comes from our, you can think of it as coming from the generated distribution. So again, you have these two things, one real data, if you will, or coming from our original data distribution, and then the generated data coming from our variational distribution, right? So even though in an energy model view of the world, we call it E, but that is in a sense the same as our discriminator from our traditional equation for GANs. So what we end up with is max of theta min over Q phi, because we are minimizing from an energy perspective. So Ex over the P theta minus, and you can, it's actually E theta, but that's like the discriminator, and then Ex from the Q phi distribution, that's the generator distribution. And again, you can view E theta as the discriminator, and then this is just minus log of Q phi of X. That's the definition of the entropy. So the point he makes is if we derive the GAN from an energy model view of the world and kind of push through how we would use the normalizing constant and how we can use sampling in order to estimate the normalization constant, because computing it even for small samples or small dimensions is very high and therefore impossible to do. We tend to approximate it. It ends up with a GAN equation, and not only does it end up with a GAN equation, he says in many other derivation of GANs, what you will see are people introducing after the fact the need for this entropy term, if you will. And in order to say, oh, they bring in this term to say, oh, GANs often suffer from mode collapse, and so we need the mode collapse not to happen, and therefore we introduce the entropy term. But what he points out is if you derive it from an energy model perspective and just cleanly push through the equations using the math that we have done before, then this entropy term comes out naturally from the derivation. You don't have to kind of artificially insert it and say it's required. I mean, it kind of appears naturally from this clean derivation of the GAN equation. The problem though, so in other words, the other way to think about it is that the generator also has to do something additional traditionally in a GAN, which is we have to maximize the entropy of the generator distribution. And so that comes out naturally from the derivation when we view it as an energy model. The thing to recall though is it easy to compute the energy of this distribution Q of phi? And the answer is generally it's not easy to just, again, so, you know, we have kind of pushed our problem of computing Z through some mathematical techniques into something that we can estimate. But even what we can estimate has a term that's hard to compute, which is we are left still with the problem of having to compute the entropy of the generated distribution, which again is not easy to do. But this is something that for some kind of models is easy to compute. So for example, it says, you know, if you just have a classifier and a discrete output classifier where the output is typically a softmax, then you can compute the entropy of something like that quite easily. That's one instance in which the entropy of a distribution can be calculated. The other example we can think of from what we have studied in the past is that of a pixel CNN. So if we move forward. So you can think of the discriminator, as we have seen, I think, in a couple of examples that Mochen discussed as well, I believe, that the discriminator we choose to be kind of compliant in an energy-based model view of GANs is that it could be a pixel CNN. Why a pixel CNN? Well, because the pixel CNN, if you recall from our discussions, every output is basically a softmax as we go through all of the dependencies down the stack, right? So that's another case in which every output is a softmax, and so every step along the way when we generate a pixel, we can kind of compute the entropy. And then to compute the total entropy is just a matter of computing and summing the entropy as we go down the steps. But even that is more of a research project, as he points out later on, in the sense that nobody has actually, or there are very few discussions or implementations completely focused on this kind of model. And the challenge when we use a pixel CNN as the discriminator is the fact that we understand from the detailed discussion of pixel CNN that sampling of pixel CNN is non-trivial to do, right? And that means in this case, because we are using it in a GAN model, we have to generate a bunch of samples. And that in turn, given that generating samples from a pixel CNN is not the easiest of things and takes a lot of time to compute, that's the challenge in this approach. That means that any approach which implements this technique will need to struggle with implementing the entropy, which means we'll need to implement pixel CNN as a discriminator, because there the entropy can be calculated, but the pixel CNN is compute intensive when we want to sample. So the point that he tries to explain is, this is still a research area at least 2 years back when he was teaching the course. So do not know whether things have changed significantly, but that's kind of the energy model explanation. And the challenge is, if you want to be consistent with the energy model and come up with a full-blown implementation, what kind of issues you will encounter. The thing he talks about, though, and I'll post a link, you can also download this paper. Apparently, this paper is excellent explanation of GANs. It wasn't published. It was apparently some note. And for reference, I looked into who this guy is. It seems either the director currently or past director of OpenAI Foundation, and has, it seems he wrote this paper way back in 2016, or actually not even a paper, but kind of thoughts. And what is impressive about this, I haven't read it, but it seems like something worth spending some amount of time on, because the lecture points out that a significant number of things that in the GAN domain that came later, such as Wasserstein GANs, spectral GANs, and as we've seen in the last lecture, or even when Mochen covered it, the GAN theory, how we deal with kind of making the discriminator a little less powerful by regularizing it, and things like that. A lot of those things which came later were kind of foreshadowed by this paper, which means this paper had ideas that which seem to hint at or point towards things that came down the road. And he says that this is one of the most comprehensive explanations of GANs and of much of the, if you understand the theory of GANs as explained by this paper, it also points to what is to come down the road, which makes it even more of an interesting explanation. And then he talks about, a couple of more recent papers that have been written from an energy-based probability estimation. As I mentioned, Jan Lukun is very gung-ho about the whole energy-based explanation, not just in GANs, but in general, the energy-based view of machine learning. And let's see, and these two papers, they talk about the challenge that we referred to towards the end of how you would model the entropy. So as we have seen, one of the ways to do it is to use pixel CNNs, but given that flows are again a generalization of that idea or the next step in that idea, then this is FlowGAN, which uses the concept of flows and tries to implement it from an energy-based model perspective. So these two papers tell us or talk to us about the approximate implementation of the entropy from our entropy part of this equation with the traditional GAN equation, because you're maximizing on one side and minimizing on the other over an adversarial kind of loss. Okay, so that kind of, again, as we go towards the latter part of these lectures, you can begin to see, they just introduce the concept, kind of give you the basic principles, but then given it's a PhD course for PhD students and research projects, kind of point towards some domain or some areas where future work in this domain can be done. So for example, towards the end of the lecture, he talks about, hey, one of the things that you can take on as a project is actually implementing a pixel CNN as a discriminator and then trying to figure out what are all the challenges and how you would reduce the time that it takes to sample from a pixel CNN in the within this implementation framework. And that would be an interesting thing because nobody has done that yet and figured out all the ways to work around that. The next set of topics is again an introduction to some view of the GANs in light of this theory. Again, I'm not an expert. If somebody else is and would like to say a few words, please chime in. That's GANs viewed in the concept or within the concept of optimal transport. So what does this mean? And then he explains the GANs and their implementation using two techniques from the optimal transport theory world, if you will, and that's implicit likelihood models, and within that, moment matching. And we'll kind of at least become familiar with what these terms are and how the GAN theory can be explained from an optimal transport view of the world. So with that, let's jump into that topic. So I believe Mochen had covered this explanation somewhat in the lecture that he gave 2 weeks back, and that's the concept of Earth mover distance. And what I took away, and this may not be an exact explanation, but intuitively it seemed to be more of, if you have 2 distribution, how much, and think of kind of them as piles of dirt or earth, and then it's a question of how much of the movement of one pile needs to happen to the other pile in order for the piles to be similar to each other, or for the distributions to be similar to each other. That's at least my kind of intuitive recollection. It may not be precise, but you can go back and listen to where Mochen touches on that aspect of the Earth mover distance, and that's relevant in this Wasserstein GAN, where the 2 terms that we're looking at is the real images probability and the generated images. So what this equation says is that we want to measure some distance between the x's and the y's, right, through some distance metric. And this equation in effect says that if you take permutations of x and y, where x comes from the real images distribution and y comes from a generated image distribution, and you take infinitely many samples from the real distribution and the same thing from the generated distribution. And if you could find the perfect permutation of X to Y, and after you have done the perfect permutation, that means you have matched X and Y to the best extent possible, then in terms of mapping, not in terms of exact identity, but in terms of mapping, then the distance that remains is some sense what is this equation is trying to say. That is, in practical terms, try to match every image in the real to its equivalent, if you will, from the generated distribution. So closest neighbor in some sense, again, in some distance kind of way, and then see what distance is left. So if we do an exact match, if we find an exact match between the real distribution, between an image in the real distribution and an image in the generated distribution, then the distance left is 0. And if we don't find an exact match, we can just get it close, then some distance, let's say D is left from that image, and then you add up all the distances that are left from the distributions, and what you end up with is kind of the what you're trying to optimize. So that's what this equation W of PRPG translating to this right-hand side is actually implementing. So mathematically, while it's represented as this, what it's practically doing is trying to map every real image to its closest neighbor in the generated to some metric like a distance. And if it's an exact match, there's 0 distance left. The distance that's left, the sum of the distances that's left, then is what is our kind of GAN equation. In practice, what the Wasserstein GAN does apparently is it doesn't deal with this problem. It kind of deals with the dual of this problem. Okay. Now, in terms of what this particular approach of what is called optimal transport GANs do is, instead of solving the dual, they kind of try to think about, what if I solved this equation itself in some way? And that's what is referred to, apparently, there's research into solving this equation, if you will, directly, instead of the dual, which is what the Wasserstein GAN does, is referred to as optimal transport GANs. Okay, so practically what the thing that you're trying to do by the optimal transport GANs is try to bring the images, so the generator in these kind of GANs tries to bring the real image and the generated image closer together in some metric, by some metric, say of some distance metric, while the discriminator tries to keep the two apart. Okay, and the metrics and the methods by which we do that are this implicit likelihood and the moment matching. So moment matching is the metric and implicit likelihood is kind of the method by which this theory of optimal transport GANs is dealt with, and we understand it conceptually as kind of doing that, instead of working through the dual, working through this equation representation of the GAN. And he refers to 2 or 3 papers that tackle this and view of GANs, and he just kind of goes through one particular example, or a couple of ways. There are apparently more ways than what he's discussing, but he takes one example of a method and a metric and kind of takes us through that. So what are implicit likelihood models, right? So the implicit likelihood distance model is to look at the data set and a sampling mechanism for the implicit models. So what, this is the whole algorithm, but what we essentially end up doing is sampling from the generated distribution. Remember that there are two distributions. One is the actual data and the other is the generated distribution. So you sample from the distribution and then pick a random batch from your actual data. And for every I belonging to S, which is the data, and the G, which is the generated distribution, you try to make the distance metric the smallest. So that's why this rho of I becomes the argmin of this, which means that we make this distance smallest and then go through an optimization to move the generated image closer to the closest real image, which is again drawn from the random batch from a data distribution. The question then becomes, okay, we can do this, but what is our definition of distance by which we move these things closer to each other? So when we say closer, what do we mean? How do we determine some two distributions are closer or farther apart? And so this is the overall algorithm, but we need a measure of how close the distributions are, right? So this is the implicit maximum likelihood estimation procedure. But for that, we need a metric by which we measure the distance between the distribution. And that metric comes out, or we use, one of the metrics we could use is moment matching. What is moment matching? Well, it's just a fancy name for basically calculating some statistics of each of the distributions. Is there any questions? Let's see, PDF and slides. Actually, Yuri, it's actually all of the slides are part of the original GAN lecture. So there isn't a separate set of slides for this part. It's all included. There are that's why the slide count is very high. It's all included in the lecture set that Mochen started with.
Yeah, thank you.
Hope that. Okay, so moment matching is just, again, yet another, Jeremy, if you've heard of FastAI course, and Jeremy, he often talks about, the jargon that's used is pretty heavy. It is, again, I view it as another jargon word, moment matching. It basically says, take some statistics and use those statistics to compare two distribution. If they said that, then I would intuitively grasp what they're trying to do, but then they have to introduce a new term called moment matching. And that means match the moments of the data and the model distribution. And basically, as you'll see in a minute, the moment just says, this is just take the average, which is the mean of the X. Let's say X is your real and Y is your generated, then take the mean of the real and the generated, which is just the averages of the two, and kind of bring them closer together. And then you can do the same at higher and higher. Obviously, the mean is just the first order. You can go to standard deviation, and then you can go on to compute this for high dimensional vectors where xi can be 100 dimension and xi prime can be another 100 dimensions. So you're kind of comparing two vectors. And here you're taking the dot product of the two, which is the transpose multiplied by this. And for those of you kind of have seen this particular trick before, there is this thing called the kernel trick, which is very much used. If you are not familiar with it, again, I'll post some link to it. It's often used in conjunction with the SVM technique, the kernel trick, because what it essentially says is there are things called these kernels that if they satisfy some property, then even if xi and xi prime are infinite dimensional, you can compute the distance between these two vectors, provided the kernels kind of satisfy some constraints, and make sure that you can compute the distance and moments, which in this case basically means the distance term between these two vectors, without actually having to translate the vectors themselves into the infinite dimensional space. So that's just what the kernel trick does, and you can learn much more about the kernel trick in several different good write-ups on the web, and I'll post a link to a couple of them. But again, it's kind of fascinating to see that how some of the techniques we learned, like importance sampling, variational distributions, and the kernel trick, keep reappearing in variety of mathematical underlying concepts that are used to explain a variety of techniques. So here again, the point being that you can calculate the moments between the real and the generated vectors using the kernel trick, even if these vectors turn out to be of very high dimension, which they will be if you're comparing images, for example, and so on. So using the moment matching technique within the implicit likelihood method methodology tells us that we can kind of address the GANs and implement GANs in this way. And he just says that there's a lot more theory of the mathematical treatment of these techniques than what he intuitively explains in the last several slides. And one of the issues with this whole approach is you will have to kind of smartly pick the kernel in order to get the best results. So you've just kind of shifted the problem around to one. Earlier we were dealing with, okay, how are we going to determine or implement a network from which entropy can be extracted easily? And initially we started with Z and the energy model and said we couldn't compute that, so we kind of introduced some approximations, but then we are left with computing entropy in that method. Here we're kind of left with the problem of choosing a smart kernel to get the implementation done in this methodology. And he talks about there are some papers where this particular way of interpreting GANs is actually implemented by this paper. And then he shows some results. And even as he shares some results, he says, look, I mean, at this point, and that's, in fact, to a certain extent, that's the fascinating part of this course, is because it is a groundwork for PhD students to launch their research projects and possibly even write papers about it. The interesting thing is he says that this is not, at least as of the writing or as of the teaching of 2 years back, one of the best methods to implement GANs. But the reason he wants to introduce this is it's always possible that this research approach, while not the best at that point in time, when combined with some of the other techniques that we have talked about and or some things that the students may think of, might help to take this technique to some state-of-the-art results and so on. So that could be an interesting research project. And he says, that's the reason I'm kind of introducing this. It's not one of the most promising techniques. You can get much better results on, the phase data sample as well as MS samples with a lot of the other techniques we have discussed before. But the reason to introduce it is a completely new way of thinking about the problem. And you could potentially combine this with some other things you can think of and get some neat paper write-ups and or research projects done based on. So that's kind of where he leaves the optimal transport approach to GANs, which consists of implementing, conceptualizing the problem as one of mapping the real distribution to the generated distribution point by point by some metric, trying to get them closer using the generator, and the discriminator trying to keep them apart, and then playing this two-player game and kind of playing the adversarial laws of one against the other, but viewed from the concept of the implicit likelihood. And then how would you determine the distance between the two? That's where the moment matching, or basically statistical properties of these two distributions, comes into play. Right, and then you can use the kernel trick in order to practically implement some of the math behind it. Right, so that kind of these last few slides is, besides the energy model, is another way of thinking about GANs and the theory behind GANs and an implementation of GANs approach. Any questions on these two things we have discussed so far? And what it's, as I said, he says, hey, this method doesn't even scale beyond these things. It needs some challenging implementation technique, autoencoding, larger mini batches, mixture of kernels, and so on and so forth. But, you know, and not even the best implementation as of 2 years back, but it's a new or a variant of what we have discussed so far. Okay, the next couple of uses of a couple of things he wants to talk about before wrapping up the GANs portion of the lecture and moving on to the homework and fun is, and I at least personally have found this very fascinating, is the other uses of adversarial loss. And the two uses he talks about is of transfer learning, although you know, I think we'll have to dig into the papers, if you will. And again, he just introduces these concepts of how potentially you can use it, but he doesn't kind of get into the very details of implementation. But again, fascinating areas of research and or follow-up of the uses of adversarial loss from the whole GAN theory. And let's look at what that is. So, oops, something. Okay, so this is again a paper where he just uses one slide to introduce the paper. There's probably much more to the theory and the implementation, but he just kind of, again, intuitively expresses what the paper is trying to achieve. What is, in this case, we have two sets of, let's say, images. One is simulated images and other is, let's say, images from the real world. Okay. Simulated images, since we are generating them, can have a lot of labels. The real world images won't have the labels. The idea of this technique is these two networks are exactly the same until we get to the adversarial loss, right? And the goal of this adversarial loss, which is our traditional GAN loss, is to make these images resemble these, and actually vice versa, to make these images and these images kind of resemble each other. Since they'll end up resembling, it doesn't matter which way you go, but conceptually the idea is to bring these two sets of images closer to each other, right? So the point is, in the feature space, right, I want this loss here that kind of, sorry, the loss is actually here. This feature space representation that results from these two sets of network, we want, using the domain loss, to make the feature space as close to each other as possible. That is, use the loss to not be able to distinguish between the hidden layer features from this network and the hidden layer features from this network. That conceptually, what it means is this network tries to eliminate anything in either of these which is uniquely identifying of the source from which it came. So in effect, he gives some examples. He says this is something that you could use, for example, of indoor versus outdoor images. Now, again, thinking about it, and I haven't read the paper, but you would probably need the objects to be the same and just being indoor, outdoor. That would at least be my guess, because if you are comparing completely unrelated images, that would be kind of hard to do. But if you're comparing similar images in content, but one is indoor, one is outdoor, and you want to kind of make them the same, then it would try to kind of see, make them the same, right? So he says this is a technique to align the data, quote align, because that's where it'll be interesting to see to what extent are they able to achieve the alignment, right, between two different domains of data that you have collected, and at some level eliminate the dissimilarity between them. And then if you were to proceed further to use the output of the thing that we have optimized using the domain laws, then we are building on, this classification loss is built on top of this, and therefore we are building on only those things which are shared between these two sets of images. So by using such a setup, it tries to eliminate anything that distinguishes the two, pushes the two things together, and then you can kind of use subsequent processing of such a result where these two things, the differences between them are being eliminated, so that anything we build on top of it is built only on what is shared between these two values, between these two distributions. I think that's a fascinating concept of usage of the adversarial loss to push two things together. So all these things you can see are just, once you have the GAN set up, what kind of applications and or explanations you can put, and then once you have that mode or that kind of an application thought in mind, then how do you drive that forward? So in this case, the thinking is, if you have two sets of images, one labeled, one unlabeled, if we put it through an adversarial loss, what we are trying to do, or what we will get as a result, is we will get these two things to resemble each other, which means we are kind of eliminating the differences and highlighting the shared content. And so anything built on top will build only on the shared content. That's a fascinating example of this that he talks about in the next slide. Again, I believe there are papers, but I'd have to kind of, you'd have to go and look at the appendix where he posts a lot of references in order to dig out the particular reference that he's talking about in this case. But this, again, he says that while this is the technique that we'll be discussing is not necessarily the best or 100% proven reliable, but it is a possible application of, again, the adversarial loss setup and the GAN networks for a real life problem. So what's a real life problem? Well, let's say we are trying to make a decision about some variable X, and we have a machine learning tool which decides the decision we are trying to arrive at is what mortgage rate to provide to a customer. And the customer has several parameters associated with him or her, and those are the variables X. And we take things through a neural network, and it spits out the decision saying, yep, this is the mortgage rate that you can give the customer. Now, one of the issues with this kind of a technique, for example, is there are legally protected classes and stuff. So there are certain parameters that you cannot use, certain variables within the X vector that you cannot use to make a determination of the decision. For example, race cannot be a factor in whether what mortgage rates you provide. Another possibility is age cannot be a factor. Sexual orientation cannot be a factor. But let's stick with race as an example. He says to decide. So suppose we say, oh, I'm just going to eliminate race from this, from one of the variables in my X. Now I'm good to go. Am I really good to go? Well, the problem is that there are many other factors that come into X, such as, for example, at least in the US, the postal code, which refers to the the code where the person is living. Another could be the name of the person. A third could be the the high school or the college the person went to. Things of that nature, which are correlated in some very strong ways with the race. So even though you've eliminated the direct race variable, you have not in your decision eliminated implicit variables which are strongly correlated with the variable that you're trying to get rid of. So what does this mean? Does it mean that I cannot use anything then as input? Because most variables that I'll use will end up being in some way or the other possibly correlated with a variable that I'm not expected to use in my, or I'm not supposed to use in my primary decision. So then you use this adversarial loss concept and this thing we have just kind of intuitively understood from the previous discussion to say, oh, I fork off at some point and use this second network to actually explicitly predict race, the variable that I'm not going to be allowed to use here, and make this the loss of this particular path very high. And what that means is, if we understood intuitively what the previous slide explained to us, if we did that, then what we're trying to do is eliminate those variables which have a high correlation with this race from being a factor beyond this point in arriving at the primary decision. Because we've just saw in this guy that if we push these two things together, anything that differs is kind of minimized or eliminated, and only what is shared is built up. So kind of an corollary to that technique is you take it, make another network, predict the thing that you are supposed not to use here, thereby eliminating from this path any variable that's correlated with this variable. So what you end up using here are things that are in X, not correlated with the prevented variable. I thought that was kind of a very clever and at least intuitively explained fascinating use of fairness from a GAN, or not actually a full GAN, but from the use of an adversarial loss for this kind of concept and an implementation. Again, you know, you would probably have to go look at the details of a particular paper to see where this has been applied in fairness, but I'm sure, you know, since he talks about it, there's probably research papers that talk about this methodology for implementing fairness. So this has again become a two-player game, right? The player one is solving the original problem, while player two is trying to kind of solve an undesired problem in order to eliminate the undesired variable from the set of variables, or correlation between the undesired variable and anything in the data that's correlated to the undesired variable, in order for those variables not to be a factor in a primary decision. And it has all kinds of disclaimers saying, hey, I'm not saying this works perfectly and so on and so forth, but it's just that this is again an area of research of how adversarial loss has been potentially used in the domain of fairness in machine learning. And this is much more comprehensive approach than just saying, oh, I get rid of some factor that shouldn't be a factor in my decision, because that doesn't actually completely remove that factor, because you may be using other factors that are very strongly correlated with a factor that you should not be using. And this methodology at least tells you that you have done more to eliminate correlates of the unusable factor. Any questions? Okay, and then we are off to kind of the last portions of GANs, and that's again very fascinating. I mean, there are people like Arto and Mayank who can probably talk to some of the details in this last section much better than I can. So feel free to chime in when we get there, because this is application of GANs in a reinforcement learning world, if you will. And I believe there's a whole discussion later on about unsupervised learning in the reinforcement learning world, but this is just the application of GANs in that or adversarial laws as applied to reinforcement learning. So again, he talks about imitation learning only in a very broad term. He says we'll learn much more about the specifics of what this means later, but conceptually, it seems to mean that what you're trying to do is to imitate an expert. There may be much more to it than that, but for the purposes of the rest of the slides, we can just think of it as using GANs and trying to learn what an expert would do in some world, if you will. So this paper, by the way, and this implementation of GANs in or generative adversarial laws or generative adversarial, and then its use in imitation learning is actually done by one of the teaching assistants of this course. It's here, his name is hidden, but it's Jonathan Ho. And his paper Gale, and then there is a variation of it we'll discuss called Whale as well. So once again, we see, much like we saw the actual equation of GANs in an energy-based model view, and this is in the view kind of policy gradients and policy for reinforcement learning. So he says, think of what we are trying to do here, by the way, just to set up the problem, is we have an expert who is doing something really well. And let's say the policy that the expert follows is illustrated or represented by, and the pi represents the policy, and pi is the policy of the expert. And the analogy we should think of is the policy of the expert is think of it as a real image equivalent. And the generated image equivalent is the policy that we are after. That is, we are after generating a policy which would resemble, therefore imitate, the policy of the expert. And we are kind of viewing the GAN equation and using it to get us to the result that we want, which is, again, a two-player game where one player is the expert. So obviously that's the desired goal. And the other player, the generator, which is what we are doing, is to generate a policy that becomes as close to the expert policy as possible. And then this is the equation implemented in kind of the policy view of the GAN equation. So again, this is, the log of the learned reward, and the reward is, you're in a particular state. Again, as I said, Mayank and Ato can probably talk more about the details of the reinforcement learning, but you're in a particular state, and the policy determines, what action you take in order to move to the next state, blah, blah, blah. So the policy that we are after as a result of all this optimization in a GAN world is the pi, which is the learned policy. And the learned policy kind of appears in two places at the equation. We want to make sure that the entropy of the learned policy is high, and this is the expectation of the learned policy, and then there is the expectation of the expert policy. So the point in this setup and what is actually done in this kind of a setup of imitation learning viewed as a GAN problem is the discriminator is trying to distinguish the trajectories or the traces, that is, given a state and what actions you would take. So it's this trajectory, I assume, is a sequence of state action pairs. Is that approximately correct, Mayank and Otto?
Yeah, I think you're explaining it quite concisely, so it sounds good to me.
Okay, and so the point is the discriminator tries to distinguish from a demonstrator versus what we are trying to learn, right? And the goal of it is to make the learn policy kind of not different from the demonstrator. The demonstrator is just another word for the expert in this case, right? And again, you can begin to see the similarity of the expression of various ways. These are just all various different ways of thinking about the GAN equation and applying the GAN equation, right? This is, you can see that it's also very similar to the energy-based GAN model formulation, right? We saw the same setup. The only thing different was how we viewed the discriminator and the generator. In this case, we view the discriminator or the demonstrator. The discriminator is basically, having an expert or a demonstrator which says, here is the policy or the trace from the policy that we would like you to follow. In a generator, while starting somewhat randomly, would want to eventually begin to imitate the trace that you get from the demonstrator, which is the expert. Okay. So in effect, the discriminator will try to distinguish the expert traces from the generated traces, and the generator will try to generate traces which cannot be indistinguished, or I should say, are identical to the expert. So that's how the two-player game is played. In this case, the discriminator is trying to keep the two separate. The generator will try to push what we want to learn to be as close to the expert as possible, right? So we try to improve the policy, just like we would try to improve the generated image to match the real image. We try to improve the generated policy to match the expert policy, right? And this is, I guess, the algorithm that is actually implemented in the Gale paper. And you take kind of the trajectories, the tau and pi theta I is the current policy, and then you update the discriminator parameters and then take a policy step. I think this TRPO apparently is some kind of, I think trust region policy optimization is at least what the acronym stands for. It's a particular optimization technique, I imagine, in the policy world of reinforcement learning. And this is, again, if you think of it conceptually as equivalent to what we looked at before, this is kind of like the implicit likelihood method that we talked about. So this is actually the algorithm that we use in order to make our current policy get closer to the expert policy, right? And then the results of implementing this kind of an approach is what they have shown in the evaluation results here, and they seem extraordinarily good. So the two axes, just to orient you in this, is one of the ways by which apparently you judge any of these kind of techniques is, it kind of intuitively makes sense, is how many of the expert traces or how many trajectories from the reference or the expert you need to provide before your model begins to be good at doing something similar to the expert, right? So it's a metric of how fast, think of the x-axis as how fast your model learns, and the y-axis is how good your model learns. And you can see that this color, which is Gale, which is generation, the GAN approach to imitation learning, it learns really fast in most of the cases compared to the prior techniques that they are comparing themselves to. So the fact that this is steep tells you that you need to provide very few traces from the expert before this technique begins to catch on to what the expert is doing, thereby mimicking the expert. Any questions conceptually? The problem, though, he says, with this particular approach is the fact that now not only are you dealing with all of the issues of actual implementation of GANs themselves are complicated, and then obviously you have to put that on top of the whole reinforcement world and deal with the issues of, you know, policies and traces and simulation world and so on and so forth. So in other words, you know, this is a non-trivial implementation challenge, but nevertheless, if you can figure this out and implement all of the, and he says there's a significant amount of detail that we have not gone through buried in the paper, but conceptually, you're just applying a GAN technique to reinforcement learning and trying to apply some of the policy optimization, but in a GAN context. And that seems to work really well compared to some of the other techniques out there for learning or imitation learning in particular. Right. So that's but again, the challenge being that not only do you have to now deal with all of the finickiness of getting GANs to work, but you also have to deal with the reinforcement learning world where, you know, what the simulated environment or what the results of the policy are not kind of in your control. So there's a lot more challenges to overcome. The one additional thing, a variant of Gale, which they call Veil, before we see the results of applying this technique and see some examples which are pretty impressive, is, remember we learned, I think it was in my last week's lecture, about how we introduce this information bottleneck, and what it basically means is we gap the mutual information between the discriminator and the generator. And what this does, it, instead of having a loss where there's like a unitary function, we want some overlap so that, you know, the loss becomes smooth and generalizable. So there's some overlap between the two distributions, the generator and the discriminator distributions. And the way we do this is to make the discriminator, we kind of went through all the theory behind it, and the idea is to reduce the capabilities of the discriminator. So we want the discriminator to be, you do not want it to be too powerful. And the way to do this is to have the discriminator work not directly on the image, but on the latent of the generated image, right? Because once you're working on the latents, you don't have the full capability. The latents typically are somewhat mutual information shared with the original distribution. And by limiting how much information the latent has of the original, you can kind of have that desired goal of reducing the power of the discriminator. And right, this is an important enhancement to the Gale approach, which they have implemented, and that's called Veil. And you can see, you know, the VA stands for the Variational Information Discriminator Bottleneck GAN, and you use that bottleneck GAN concept to imitation learning, and that improves the stuff even further. And in order to demonstrate the results, now I'll need to switch. So give me a minute as I stop sharing. I'll go back to the original thing. You know, whether you can see my screen now. Can you see my screen with the title whale?
Yes.
Okay. So here, what you'll see in the next couple, 3 videos is basically the original, which is kind of the expert, and the policy that is being learned using techniques implemented in the whale paper. So, this is the information bottleneck on top of the Gale concept, and the Gale concept, remember, is implementing the TRPO optimization, but in a kind of GAN context. So what we're trying to do is, here's an expert who does these set of actions, and we want our model to learn the expert and imitate what the expert is doing. So that's the goal. So to the extent that this guy on your right does not follow the guy on the left and what he or she does or what this object does, then we have failed. And to the extent that they are similar, we have succeeded. So that's kind of similar to thinking of the image on the right, which would be our generated image, being identical or as close to identical to the real image as possible. That's the way to think about it as to what we're trying to do, which is implement the Gale, but on top of it, we have also implemented the information bottleneck, and here are the results. So as you can see, it's imitating really well, right? The two things are tracking very closely. Then same thing here as well. Much more complicated movements. So here's another comparison of a man walking. And here's kind of a different paper from different implementation from DeepMind. And this is, I believe, the variational discriminator bottleneck version. And so we're back. So from those So the last slide he points to is the fact that, he takes these different things we have seen so far and kind of illustrates how much better the variational discriminator bottleneck implementation, which is this guy, these guys here, are compared to even the Gale implementations. So you can see that the guy learns much faster than the whale learns much faster than the Gale implementation. But you need a lot less samples to get it to do the same thing, exactly like the expert in terms of policy. Any questions? And one more pointer, I think. Sorry, go ahead.
Yeah, I was just going to say that in imitation learning, there is a problem with the fact. So we are learning from the expert trajectories, right? So the agent actually never or like really rarely encounters the state where the like which are out of the distribution, which means, for example, imagine learning to drive from the like experiences of human drivers, and one of the problem with imitation learning is that like human drivers never actually, or really rarely end up in improbable situation, like when you're heading towards like outside of the road, right? So all the trajectories are on the distribution, and the problem is that with imitation learning, that eventually you can for example, if you run for a while in that kind of setting, right? So you probably will some error will accumulate, and you will eventually end up in a state which was not in this expert in the set of states that expert was during the training. And I'm wondering, maybe having this variational bottleneck helps with that problem, or maybe not. I guess it's
that's interesting, fascinating, because what you're trying to say again in the conceptual phase is, for example, if the sticking with your example of driving, if we just use expert, then the expert will never drive in the wrong direction on a one-way road, but potentially you can encounter that condition, and if so, you'd be lost because you're only imitating an expert. So the expert has never seen that, so you would never have seen that, and then you don't know what to do.
Yeah. So you probably don't have much like trajectories where the experts intentionally goes drives in a bad way and then recovers from that bad situation, right?
Right.
You will have to explicitly ask experts to generate those kind of trajectories, and that is not how it works usually. And so I'm thinking maybe this having this variational bottleneck somehow helps with this kind of problem, but I guess it's necessary to check out the paper for that.
Yeah, because I'm thinking about what you're saying. The interesting thing would be, because the variational thing, what it does, it takes you to the latent space. So the question, if we think of it again, sticking to the images and then drawing the analogy, is will your latent space generate those images which are not in your real domain, but which are still relevant and useful for the training, right? That's kind of conceptually what we are saying, because your latent space should somehow yield those traces which the actual or trajectories which your expert will not explicitly be providing.
Yeah, I guess it can kind of make the latent space more robust or smooth with respect to kind of this out of distribution images, for example, right? So we can kind of, if we drive for relying on the video from a camera, right? So we are kind of we haven't seen many images that when driver is going out of the road, but in the latent space, after the regularization, probably our agent will be able to kind of map this a bit, the kind of images which have led to divergence in other cases to something that is on the trajectory, and therefore we have a strategy for it. So yeah, that's interesting.
Yeah, fascinating. Right. Another way I was thinking is about it is to say, ultimately, if it's imitation learning, you can't learn beyond imitation, right? You are ultimately only imitating. So it's almost like we want imitation learning to go beyond imitating.
Yeah, true. And plus, I think so this work also helped in the stability of the GANs as well. Stability in training of the images of the GANs as well, which I think so the issues that GANs had with respect to mode collapse and all, since they are kind of regularizing before they are sending the output to in inverse reinforcement learning agent. So that kind of like it's kind of like improving it in a sense of the stability factor as well in the whale. This is the work that I'm talking about. So yeah, other than the improvements in the video imitation, I think so they have tried with the humanoid with the challenging tasks like the dance, the run, and the cartwheel. I've just opened this whale paper and they have given some conditions into the theoretical analysis and the convergence and the stability of the conditions as well. So yeah, these 3 or 4 forms. Yeah.
Interesting. So you're saying besides the results, there's also kind of methodological improvement in stability of results you get and the stability of the GANs that you're
Yes.
using as part of this.
Mm-hmm.
Interesting. That's
Because
fascinating. Thanks.
Yeah, because they try out the syllaba face generation as well with the syllaba 128 cross 128 images and syllaba HQ 1024 cross 1024, and they gave the iterations here as well. So yeah, in the paper, those tasks are helpful as well.
Yeah, one last thing I wanted to mention, which at least I found quite interesting. So if any of you are into this kind of stuff, the professor spends the last 7-8 minutes kind of going through, this lecture, I believe, is the week before when their project proposals were due. So he spends about 10 minutes of the lecture towards the very end of discussing the various potential projects, and they, meaning the course staff, has a list of things that people could be working on in each of the domains that have been covered thus far, and what has been, at least 2 years back, left unexplored and without the students coming up with their ideas, the staff themselves say, hey, just to kind of stimulate your thinking, here's a bunch of things in each of the, whether it's flow or implicit latent models or GANs or, pixel CNNs or whatever. Here are all the different things that, not all, but here are a few of the different things that still left to be unexplored that you can kind of take on as a project to do. So I thought that was very fascinating to just look at the different thoughts and ideas they had about potential things to pursue. And while that may not be of great interest, it at least begins to illustrate the kind of problems in the research space that people are working on. And one of the examples he gave that I thought was quite fascinating. Of course, he talks about bioinformatics in general and applying a lot of some of these self-supervised techniques or unsupervised techniques in that space. But another thing, and I'm probably going to mutilate the idea, but broadly speaking, he talks about one student from the prior year actually taking these concepts and applying it to database queries and and kind of extracting, and this is the part that I'm probably going to butcher because I'm talking from memory and stuff, but what I thought was fascinating is the idea of application of these kind of techniques to variety of domains is what I thought was very fascinating, because he talks for a couple of minutes about how that student applied some of the techniques that we have learned so far and tried to extract some, and I don't remember what and how, but I found it fascinating that he took these set of ideas and implemented it on top of databases and database queries to extract some very useful, relevant information. I thought that was kind of a cool application of some of the things we're learning to a domain that at least I wouldn't think of these techniques as being relevant. So that was something else the professor was encouraging, is take some of these techniques and kind of try to implement it in spaces that they haven't seen implementation in. So if you're interested, if that kind of stuff fascinates you, listen to about the last 10, 12 minutes of the lecture and you might get some ideas.
I was also thinking, according to the course schedule, we are like students are supposed to come up with their final projects ideas by this time approximately. So we are introduced to the main techniques of generative learning, I guess, and we have the last homework like coming next, and after that there are no more like programming homeworks in this course, so we will have a bunch of lectures but no assignments. And yeah, I was wondering if people are interested in or have some ideas for a project for the course, and I can share what I myself was thinking, and maybe someone will be interested in doing something similar and joining or something like that. So I was thinking about applying variational autoencoder to as ideas from variational autoencoders to text, and like I don't know, I don't have a quite clear vision of what do I want to do as of now, but something like style transfer would be interesting, and I think it's kind of related to the capabilities provided by variational autoencoder, and also some kind of independent component identification maybe some techniques might be applied to figure out the components which have some semantic meaning in a text representation, like inside the model, and that also probably might be done using some kind of manipulation in the latent space. So yeah, I'm thinking about doing something in that direction, like as a project for the course. Obviously, this course is kind of quite involved and intended for students pursuing their career in research, and we are probably not all PhD students here, but still we can do something relatively simple.
No, that's a very interesting idea. I think that's good proposal to at least solicit, hey, what would some of the, even if people didn't pursue it themselves, but even just proposing or is how I'm thinking about doing some things, and then possibly, as you say, collaborating on implementing, but having a discussion around what kind of domains and applications can people think of for some of these techniques to explore and figure out would be great. I think that would be fascinating.
Yeah, totally. So I think that everyone, if you have any idea, maybe like the one similar to what I've told, like it's not very concrete, but still some kind of direction for try things out. So please share if you have some ideas as well.
Definitely. And it's worth thinking about, because it kind of, I think even just thinking about that will make us go back through some of the techniques and kind of learn more by trying to apply them than we would have just by looking at the slides, I think. So that's a very good way.
Also, Kaggle has a competition. It's not for money, but it's called "I'm Something of a Painter Myself." Use GANs to create art. So if anyone's interested in the visual side, or the image side, there's the Kaggle.
Is that a competition, or is that something that they have kind of initiated as project, or?
I think I think it's Google's thing to promote people to use their. I posted. I think it's to promote people from using their TPUs. So you can't win anything, but I think it still has leaderboards and let's say prizes. You get more TPU time if you win. So so if you use TPU, you get more TPU. But yeah.
Yeah, I think that's a good suggestion. I'll kind of propose
just
that.
Implementing GANs in JAX would be fun. Just like re-implementing stuff that you can find. For example, a PyTorch implementation would be, I think, very useful learning experience. So by translating it from one code base to another, you will learn a lot. And JAX runs on TPU much better than PyTorch, so that makes sense to me. So that's one of the things one can try. Yes.
Yeah, I think this heavily is on style transfer, right? The beta painter. So I think they talk about CycleGAN and StyleGAN. That's going to be heavily influenced very specific on this one anyway. But at least the data is already there.
And
so.
I don't recall off the top of my head, Arto, but I think I have seen so your proposal or directional thought about kind of bringing the style transfer to text is something that I have either read or kind of seen some hints to papers about, that kind of copying the writing style of people from one let's say an essay of some size or a couple of paragraphs, and kind of applying style of a particular writer to those paragraphs.
Yeah, in this,
so that's fascinating.
like people, for example, try to translate from informal to formal text. So that's kind of some kind of, I don't know, probably also practical application for this stuff. And I know there is a company called, how it's called, they have this writing assistance, and probably they do a lot of research in this field, but they are not open sourcing stuff. So they're just a commercial product. How it's called? Yeah, whatever. I can maybe post a link later. Maybe you even used the app. Yeah, I guess also. Yeah, there has been a lot of progress in NLP, like during the last 5 years or so, and probably one came up with interesting implementation. And regarding the style transfer on images, I think FastAI has, Jeremy had great lectures, and probably they have also implementation in FastAI framework. Oh, yeah, you reposted Grammarly, the company I was referring to. Yeah, so I think there are good implementations in FastAI for the style transfer using CycleGAN or something. So if you would be interested, you can find the corresponding lecture and notebooks on their website.
So I don't know if I want, I don't know if I want to do a project, but I think I've posted a couple of links in the area where we actually do work now, where people sort of use weather and climate data and do all sorts of predictions with generative models there. I think I posted RainGAN, which Google just posted. It's not called RainGAN. It's called something else. But also people do, satellite to map data conversions. So I was thinking if maybe if I want to do a project, it will be in one of those areas. Basically, maybe take climate data and do some sort of like high resolution prediction. People do it with both GANs and flows.
Yeah, that's also sounds really interesting. I believe like the simulations of climate are still very far from perfect, right? And it's like common belief that the dynamics of our environment is unpredictable, right? Like in terms of making precise simulation.
Yeah,
so,
but specifically with climate data, they actually, like those big models give you 100-kilometer resolution. And in a lot of problems, you need like much better local resolution. So there's a technique that everybody uses, statistical technique called downsampling. So people have been trying to use generative model to basically come up with deep learning way of doing that. I think somebody actually on TWIML, there was somebody who was presenting their work on that, and they use flows. Which I tried using GANs for that before and didn't succeed, but you know, that would be interesting area to try.
Yeah, sounds like a really great idea with practical application.
Yeah, these, you know, at least that's what originally drew me to look at this course. Is definitely once you have the foundations, then this course kind of enables you to, I think, get some techniques and try to be at the edge of what's kind of being done even in research and what people are attempting to push the field forward. And so that's the thing which is fascinating. In fact, you know, another thing that I wrote or thought to myself of doing, which would itself also take quite a bit of work, but I was just fascinated. I would be interested in knowing, you know, any of these things that obviously this course was taught 2+ years back, and it'd be interesting to know, you know, how or in what ways have these techniques been pushed further forward in the 2 years since. It's like 21, and I believe this version of the course we are referring to is in 2019 spring. So, you know, while not immediately practical, I was just curious as to how things have changed, because if somebody were to ask, I don't know whether some of the fields or some of these might just be where they are. I mean, you know, like Pix or, you know, Gauguin or this or that. I haven't seen too many other things, but some other things like what Yuri Arato talked about, that might be stuff where the NLP has moved forward, you know, application of these kind of techniques to climate forecasting is something that's probably new. So, and like the professor talks about, you know, application to bio computing, and that's something else which has a lot of tremendous practical applications. So I don't know whether anybody has done work in that space, but that would be another space. If, you know, I don't know whether any of the people attending are familiar with that space, but that's another space in which some of these techniques can be very, very useful, because you have a lot less data in that space. Typically, you don't have data, and the data is also, you know, when he talks about kind of bringing domains closer together, I was thinking of like images from different CT scans and taken from different machines with different orientation. And I was wondering about, you know, what kind of things we would be able to do if we were to apply these techniques to those domains as well. Okay, thanks everybody for joining, and yeah, I'll you know, kind of stimulate, and you can do that to the discussion of thinking of proposals and then probably working together on some of those, and we go forward. Thanks for the discussion, folks. And again, if you or anybody else would like to volunteer for the last homework and stuff before we move on to other lectures, great.
Thank you. Goodbye.
Okay, see you all next week. Thanks. Bye.